Okay, thank you. So I'd like to talk, the title of my talk is Error of Errors, and I'd like to talk about the scientific sort of sense of errors, what they mean, and then I'll talk about errors in life, in biological and also social systems, and how the concept of error is very much different. So I'd like to start with random errors in science. And generally, we have three types of error in science. One is called random errors, fluctuations. And the word error actually comes from the Latin word, which means sort of wandering. So it's a kind of wandering. And the second one is called a systematic error. So if you fire a gun and it's constantly off, maybe due to the air blowing or something like that, that is a systematic error. And that's quite hard to deal with. And the third one is just human error, and we heard a lot about human errors. They can be mistakes, they can be deliberate actions to try to mislead people. And when we deal with random errors, the fundamental thing we have to consider is that random errors have a particular limiting sort of distribution. So if we measure something a couple of times, we average it, we make an assumption that essentially if we measured it 1,000,000 times, it would follow this bell-shaped curve you all are aware of, right? And I show at the top right there this bell-shaped curve called the normal distribution. And you can see in this case it's for students. So the average mark in the class is given by the point where, there's a maximum. And then we have students with high marks and low marks. But if any of you have, analyzed your class in terms of the grades, you'll find it never actually follows that bell-shaped curve, very, very rarely. But there are examples in science, when you do science, simple experiments, where we try to reduce it and where it does work. And this is one example. So at the turn of the 20th century, people didn't actually accept the idea generally that atoms existed. And Einstein, he wrote a paper in 1905, and he showed that the motion of some dust, dust particle or something, could be used to actually prove that atoms exist. So the dust particle's been hit by multiple atoms, and it's jiggling around a little bit. This is a simulation. You can see the yellow particle moves in this random trajectory. And if you plot the way the steps it moves, not the distance from the origin, you will come with this bell-shaped curve. And it's not the position, the average position is irrelevant. It's the width of that curve that proves the existence of atoms, essentially. So that's one example where we use this kind of randomness to prove the existence of atoms. Now, there are also major errors because we use theories, okay? And then we compare them with experiment. And we, go back and forward. The theoreticians change the equations to try to match the experiment, and experimentalists change the experiment to try to agree with the theoretician. This is one example which led to the concept of quantum mechanics, quantization of energy. And what you see is a black curve that says classical theory, and then you see the biggest blue curve. And what happened was, at the end of the 19th century, Maxwell essentially had equations that described how waves worked, like light. And Newton had a bunch of theories that described how objects like balls flying through the, or it could be molecules even, worked. And they used these theories to produce a classical theory of how radiation is emitted when you heat up a thing called a black body. Okay, so if you heat up a piece of iron, it will eventually, glow red and white. And you can see the classical theory did not fit the experimental result. And this was called the ultraviolet catastrophe. And it led, so it was a massive error. This is a massive error, but this error led to one of the most important changes in our thinking about science, quantum mechanics. And Max Planck, he had to come up with some idea, there are jumps. But he didn't like that idea. Nobody liked it, but it became accepted, and that's why we have quantum mechanics from this massive discrepancy, a systematic error between theory and experiment. So let's talk about something real now, more real, error in RL, okay? If we look at, let's say, one of the things I look at is how soft cells are. And so we took some cells from patients' lungs, and then we measured the stiffness using some nanotechnology, okay? And what we find, this is a whole bunch of different people. Some of them have metastatic cancer, some of them don't. They have to go in every so often to check for the fluid in their lungs, pleural effusions, and we take those cells. And what you can see is if you look at the bottom curve, these are normal mesothelial cells. They don't follow a Gaussian or normal distribution at all. They follow another distribution. But you can't say the cells are in error. This is just a fundamental aspect of life, that there is a distribution. However, if you look at metastatic cancer cells from these patients, that's the curve B, what you see is it actually looks like a Gaussian. So the real good cells actually have this weird broad distribution, and the metastatic ones do follow some kind of normal distribution. Now, if we look at complex systems, and I'm very involved with complex systems, there's two types. Structurally complex systems, things like a watch, things like robots, or robots that build computers, all these things are structurally complex, but they have very little freedom of action. And so we can analyze those, and we can use this kind of concept of error analysis, you know, the normal distribution. We can work out, oh, the gears have a certain amount of play in them and so on. However, that applies only to really specific elements of technology and engineering. The second class of systems, which is by far the biggest, these structurally complex systems account for a very small part of our universe or our world. The other one is interactively complex systems. That is where systems interact with each other. And this then interacts with this, with this, with this, with this. And in such a case, we have a greater freedom of action. So when we do this type of analysis, the statistical analysis, the concept of error completely breaks down. It applies to networks, things like Facebook. It applies to networks like the planet Earth, to earthquakes. It applies to everything that's actually real in the world. And when we analyze those, if you look at the right as a particular scale-free network, we see we don't have an average earthquake. We don't have an average anything. We have a whole range of behavior. And this shows some of them. Modern banking, there's not an average kind of bank. There's big banks, a few big banks, many small banks. The way the US airline system works has a few very strong nodes, as many neighbors. There's no average number of movies an actors are in. Some are in, you know, all the movies. The other ones, like in Hollywood and Los Angeles, where I am, everybody's a kind of wants to be an actor, right? Maybe they've been in one movie if they're lucky. So the distribution's completely different. And it applies to all these phenomena here. If you look at earthquakes, forest fires, solar flares, extinctions, wars. There are a few big wars and many small wars. And it follows this thing called the power law distribution. And you can't say there's any average there. This is like the powers of 10 versus the powers of 10 here. And if you look at the human brain, neurons, they also do this. So if you look at MRI, functional MRI activity of the brain, you'll find that it also follows a power law. There's not an average kind of brain activity. It doesn't exist. If you look at neurons firing in neuronal cultures, they also follow this behavior. If you look at EEG, it also follows this behavior. So the concept of error in the real world has no real meaning. There's no meaning, in my opinion. And our work actually is to try to develop a machine that's completely imperfect, a type of computer that actually emulates the brain. And this is activity in the brain, resting state, fMRI, and this is our particular machine. And it never does the same thing. I believe that in trying to look at complexity, scientists are very, very badly equipped. Scientists can't look at complex phenomena. They want to keep away from it. They hate it. It gives them headaches usually. And it is the biggest single challenge of the century to understand complex systems. And in that respect, artists have a terrific role to play because artists look at very complex phenomena and they're able to extract some kind of information from it. And this is a particular example, birdsong diamond, which is, I think it relates to artificial life, which involves, it was showed last year in Ars Electronica, evolutionary biologist Victoria Vesna, who's an artist, and Takashi Ikejima, who is working on these networks. And when he found that, for instance, when you have 1 million object voids, you start to get emergent behavior, and this thing starts to come alive, this life. And this thing is based on that concept. So, in summary, I would say error is a thing we use to describe what we don't understand. If we understood the very sources of what goes on, it wouldn't be error anymore, okay? And the concept of error has, at least from our mathematical sense, has little meaning in the real world because the real world is intrinsically diverse and dynamic, and the emergence of things can't be predicted. Particularly in the world of networks, interactions, and so on, it's, to me, meaningless. And the inevitable, the unpredictable, are things that arise from the interaction of objects, not the behavior of objects. The behavior of the object itself, like you saw, it follows that bell-shaped distribution. But when you put them together, you start to get something that resembles the life of the planet and our own lives. So thank you very much.